Good morning, everybody. Afternoon, evening. We're going to get started here. Just 1 second. I am trying to finish up where things are on my desktop. Give me 1 second. We'll start in just a minute. Thanks for joining. Be right back. Okay, hello everybody. We are about 3 minutes past the hour. I want to get started here on our session today. First and foremost, thank you all for joining. Thanks for taking time out of your day to join this session. It's a little bit of a generic session on asset transactions, something that I think is an important concept and important topic, but honestly, when I was a developer, I didn't think about this a whole lot. So this is just an effort to kind of, let's educate on kind of what some of these things are, just talk through kind of how these things work, right? So, but before we get started, as with every session, we do like to kind of characterize what kind of session this is. This is kind of beginner to intermediate. We're going to get into some algorithms, some concepts here about, how do you do these things in distributed systems. We're going to go through some of the problems with some of the isolation levels in a database. But the beginning of this really kind of basic stuff. And it's stuff that I think a lot of people should be familiar with. So we have a few topics we're going to cover, but I would love comments and questions from everybody. Please, gosh, by all means, enter your questions into the chat or the QA. I've got it on a second screen over here. I'll be monitoring that along the way, and I'm happy to answer questions. And before anybody asks, the recording will be available a little bit later today. I know we stream these things to YouTube, and if you ask questions there, then we'll get the questions into here and all that stuff. But it's pretty much on our channel almost immediately when these things are done. So hello everybody. I'm Jim. I am a principal product evangelist here at Cockroach Labs. I've been at this company for, gosh, man, like almost 4 years now, and been in data really for quite some time. Now, I will talk about these concepts at kind of an academic level, and I'm happy to take questions and talk about these things at any level with you as we go along the way here. So you can follow me. I'm at Twitter as James and everything. If you want to ever reach out to me here at Cockroach Labs, it's just Jim at Cockroach Labs as well. So, okay, so let's get into this. So what are we talking about here when we talk about transactions? And if you just look at it at the most fundamental, smallest way of thinking about these things, a transaction really it consists of 3 phases, right? There's something says I'm going to begin a transaction. I'm going to execute the transaction. I'm going to commit or roll back the transaction. So basically, I'm going to commit it like everything went well, or I'm going to roll back because something went wrong, right? This execute the transaction thing, when I do, select star from customer where name equals Jim, whatever that is, in SQL, and if SQL is a pretty damn powerful language, that's actually going to get broken down into a couple different statements in that execute transaction phase, right? So 2 here, like the second stage here, could be, a couple lines, it could be a couple different commands, it could be like 15, it could be 30. There's a whole world of complication in terms of how databases execute things underneath the covers. And, there's a whole kind of concept around cost-based optimizers and when these things get done and how you I'm not going to get into kind of how transactions are constructed in a SQL engine, but it's important to kind of understand, at the top level, how these things kind of come together, because I think this is the core of some of the issues that people find in databases today. So when I'm doing this 3-step thing here, what could possibly go wrong? Well, what happens if I begin a transaction and only half of it was successful and something failed? What if 2 transactions try to go at the same time? What happens when one transaction has to wait for another? What happens when something fails, but a rollback in one transaction is causing a rollback in another transaction and in another, like there's this cascading rollbacks, like lots of things can go wrong here. And the devil is in the details when you build a database. So, this is kind of one of those reasons why, I think it seems like pretty basic technology building a database, right? There's a language, there's an execution engine, and then I got to store data to disk, right? Like pretty simple. It's the corner cases that can go wrong in transactions that kill you. And I think this is the place where database engineers and database developers spend a whole lot of time, because this is tricky stuff. And so that's what we're really going to talk about today. So we're going to talk about ACID. I'm not talking about the drug. We're talking about the concept in computer engineering, right? And so the concept of ACID has really been around since 1983, and it has been kind of the core when we think about the transactional model in databases. Like everybody says, like, oh, ACID transactions. And I'm not sure everybody totally understands these things. Now, this paper is fantastic. If you want to read the original paper, it's great. But it defines ACID as a set of properties of a database to guarantee validity in an event of an error, power failure. It basically abstracts away issues out of the database. Now, there's another thing. It was called base at the time. I know ACID versus base was something that we talked about in the 2000s, and base really became kind of this eventually consistent principles, and kind of what that is. And so you think about NoSQL databases, they're kind of more base, BASE, if you want to look that up, right? But we're going to talk about ACID in terms of transactions today, right? So it goes all the way back to 1983. These concepts have really been with us for really quite some time. So Atomicity, let's just go through the four things here quickly, just to give a base set here, right? So basically, Atomicity is about the atomic unit. What is that transaction? The transaction is select star from customer where name equals Jim, right? That needs to execute in its total or not. You can't have half of it. You can't have a quarter of it or a third of it. Like the atomicity of the transaction is basically that transaction in its whole. So just put a hard line around that, and that's atomicity. So you need to guarantee that the transaction is the transaction. Sounds simple enough, right? Consistency really is less about the consistency of like across the transactions. That's more in isolation. We'll talk about that. But basically, this is like, don't violate the integrity of the database. Like each transaction will leave it in a valid state. And so when I think about consistency, I think about things like referential integrity and foreign keys, these sort of things, like the things that make sure that the data is correct. Now, there's a whole lot of things that we do in our transactions and from an isolation point of view that also kind of contribute to consistency. But I think about this as like the data is correct. Like, the data types are correct. The integers are stored as integers. Strings are strings. If I'm going to reference a customer table and I have a customer ID and that's going on to an order ID, then I need to make sure that that's going to be correct. Now, that doesn't happen in all databases. I mean, implementing referential integrity in different databases. In the pure relational databases, it's definitely, it's kind of standard, right? It's you have primary keys, you have foreign keys, like secondary indexes. You have a lot of tools to actually guarantee that, and the database takes care of that for you. Now, in some of the NoSQL databases, you don't get that. You kind of have to code it in, and that's a wholly other session. But kind of the differences between those things. This is where consistency is actually pretty important, right? The integrity of your data. Now, isolation is where we're going to spend a fair amount of time today. Isolation basically ensures that transactions will leave the database in the same state as expected, right? Like if I execute a transaction and I want to write, insert Walker into customer table, well, that's got to work. And if it comes back and I select, that row and it comes back with Miller as the name, something went wrong, right? And so like, what happened, right? And so the consistency and the integrity of the database is really built into the isolation of transactions. And we're going to spend a amount of time on that today. And then D in ACID is really about durability. So no matter what happens, the transaction commits or it doesn't. So like, say I'm going halfway through a transaction and a backhoe goes through a cable out in front of the building and the power goes out or the internet happens. And so that rollback has got to happen. So the durability of the database really kind of protects it against kind of a physical failure or something like that, right? And so that's kind of the four key concepts here, right? Atomicity, consistency, isolation, and durability. And so that's really kind of the definition of ACID. I think many people just kind of overlook what these things really are. Oh, do you have ACID transactions? ACID transactions. That thing has ACID, but they don't really understand, like really deep down, what these things mean. And this is what I want to talk about, right? And like, I think this is the area of ACID that I think is pretty important. Now, The I in ACID has various different levels, right? And it's a setting that you can actually put on your database. Now, geez, man, when I was a developer, the last thing I thought about was an isolation level. I just used the default level of whatever the database was. Now, Postgres, Oracle, SQL Server, you can choose which isolation level you want. And there's reasons for doing that. I mean, different workloads have different requirements in terms of, you know, the isolation of transactions, how quickly they're happening, are they likely to happen at the same time, these sort of things. And so you may want to relax isolation settings from you know, the top levels, because maybe it's a performance thing, or you don't want, you know, transaction retries and these sort of things. You know, here at Cockroach Labs, we actually we are serializable, and that's it. Like, that is our isolation. Now we could do things like follower reads and some other things that allow you to kind of you know select as of a time. Like, there's some things that we can do in the database that kind of relax some of these things in terms of what data you're actually going to get returned. But that's kind of separate from really the concept of ACID today. And I just like to clarify the concept of ACID because it's pretty important. Now, if you go to Jepson.io, so Kyle Jepson does a great job talking about distributed databases over there in this link. And so if you go to this consistency, he talks about all these consistency models at length, a lot better than I can do in our half hour or 30 or 40 minutes that we have together today. So I always go there, and this is a chart that he has really that talks about, you know, really the consistency that's guaranteed, you know, from the bottom up, with the lowest consistency guaranteed on the bottom from read committed to some of the highest and strict serializable at the highest level of isolation, where you are guaranteeing correctness. And so, you know, we focused a lot of our time here on serializable, honestly. So, okay, great. So that's kind of the baseline of isolation levels. So weak isolation levels can result in some pretty common issues, right? So there's a thing called a dirty read. A dirty read is basically when, you know, I'm writing to a database and a second transaction comes in and wants to read, and the first transaction hasn't completed yet. Well, I'm getting data that's not committed, or I don't know which data I'm going to get. Was it before that transaction hit that step or not? Like, and so dirty reads is definitely something that it's pretty easy to understand, right? There's another thing called a non-repeatable read, where two transactions return different answers when you read the same row twice. And what this means is, like, basically look at one transaction is happening. It kind of goes through, another transaction reads this, and then it comes through again and reads it, and it gets a different response, right? So, and the initial response is gone. This happens a lot in lower level isolation levels, right? Now there's the write skew, and we're going to talk a little bit about write skew in a little bit, but this is where basically transactions overlap and they're trying to do the same thing. And in the meanwhile, you're kind of conflicting what you wanted to actually happen in the first transaction with something that happened in the second transaction, and you end up in a bad state. This happens a lot in like inventory systems where, you know, you're asking for, you know, to reserve, say, a TV at a store, and at the same time it says, yes, it looks great, but before that transaction actually commits, somebody else comes in and says, hey, are there any TVs? And there's not, but actually, and there is, and it says, let me come in, so you get these weird skews, and we'll go through that a little bit more in a bit. And they cause big issues in data and almost the integrity of what you're trying to do in the database. And then finally, there's these phantom reads. So, you know, like you get these row matches on search criteria, but it wasn't initially seen, right? And so like you'll get reads in one select statement that just aren't repeatable in the second. And this really comes down to when and how transactions, like the correlation of when things happen. And when things happen in milliseconds of each other is where you end up in these issues around isolation levels, okay? So here's some, these are default. So this is default. A lot of these, am I good? Okay. Let me just make sure everything's fine here, everybody. I am. These are the default isolation levels for, if somebody could just dump in a chat, just say hello, just so I make sure everybody's still there. I had something actually just froze on my machine. I hope I'm fine. These are default isolation levels for a database. Let's just do this. Let's try this. One second, everybody. I'm so sorry about this. Well, tell you what, everybody, I think my second screen has failed me here. So I'm going to continue on. And if this has had issues, then we'll come back and do it again. How's that? But my second screen has frozen for whatever. I'm using an iPad and I'm extending it here, but I don't know what happened. I'm out of my home office. So these are default isolation levels for a few databases. So Mongo is read committed. Typical, the most popular databases, Postgres, SQL Server, these sort of MySQL. The relational databases you can choose which isolation level you want. This is default, right? CockroachDB, we are serializable, and you can't relax that, right? But you can actually go up from the others. And so this is kind of by default. And I think it's actually pretty important for people to understand so that you get like, hey, wait a second, am I going to have issues with my database or not? One second here. Let me just, I just want to make sure I'm not missing any chat or anything like that so that I have this. Okay, good. Now I'm seeing it. It looks like everything was kind of in a bad state there. Thank you for people jumping in saying everything was on the correct slide. Andrew, I really, really appreciate that. So we're still live, that's good. Okay, so these are default isolation levels. And then across the top of the various different issues that can go wrong. I'm not gonna talk about cursor lost or lost updates, but we're gonna go through some of these levels right now and show some of the issues that can happen. But this is a kind of a useful chart in terms of some of the things that can happen at the various different isolation levels. I mean, take away the default isolation level from the stuff on the left-hand side, and I think it's a pretty useful chart to kind of show you as a developer, okay, these are the things that can go wrong. Now, I think it's on each of us to think about our workload and what we want to actually accomplish, right? Like, what is the nature of my data and what can go wrong and what can I be okay with? And so understanding these issues is actually one of those things. There's lots of material out there that talks about these things. So, okay, so let's just use a transaction. Let's update account balance. And we're gonna have two simultaneous transactions, right? Our account is gonna start at $0. We're gonna read the account balance. We're gonna update that balance to reflect a deposit. In transaction one, we're gonna update to $100, right? We're gonna put in $100 into my bank account. And in the second transaction, we're gonna put 50 in it. And so at the end of this, like if these two things happen in order, well, I would expect to have $150 in the bank after that, right? So this is kind of a very simple way of looking at this. So when you think about read committed, here's what can happen. And so, here's the first transaction. We're going to select our balance from our accounts where ID equals 1. Okay, great. 0. That was the first step, right? I'm going to update this account. I'm going to set the balance to 100. And then I'm going to select, I'm going to look at that. And before I commit, and this is actually, remember, there's a begin, there's the execution, and then there's the commit. But before I commit, in read committed, in a read committed database, we're going to say, let's begin this and let's update this and set the balance to 50. And then, these things happen. And it's not even committing. Only the first two pieces of this thing have actually done. And now they're actually updating that account table before the commit has happened on the left-hand side. So at the end of this, after this whole commit has happened, I select the balance and it looks like it's 50. What happened to that $100? Now, this is a very simplistic kind of outline of something that can go along with a read committed database. And this is the kind of thing that you have to start to think about, and what are the requirements of my data? And so when I think about, the transactional model of a database, and people kind of just, oh, don't worry, it's like, it's good enough. Like eventually consistent is not right. Like even if you're going to go back and resolve these things in some way, you're wrong for some moment of time. Eventually consistent just means you're just not consistent at it all the time. And it really comes down to the data and the workload that you're trying to control to see if this makes sense for you or not, right? So that's kind of in a read committed. So if you look at serializable, which is the top level, what happens basically, we have our transaction on the left-hand side, begin, we update that. And then on the right-hand side, what you're seeing is we begin, but we actually block that thing. We couldn't serialize that because there was a concurrent update going on. So in this case, you may get a failed transaction. Now, this is a really simple transaction. The likelihood here is very rare, but like sometimes our transactions are a lot more complex than this. What you're going to get here is a transaction retry. And so it's up to you in your code to insert the proper try catch blocks to actually take care of these situations. Now, I know it's a pain, try catch blocks and whatnot, but this is exactly what's going to happen. Now, what happened is the second transaction hasn't actually committed. So you didn't put a try catch block in there. it's on the code to say like, wait a second, I got to go do this again. So like I try this, it didn't work. Okay, let's just retry it as the catch. And it did work, and I would get to 150. But right now, without the try catch block, the final balance here is going to be 100, which is down here at the bottom. Okay. Now, right skews are a little bit more difficult to kind of visualize. Basically, it's on the premise of a future decision. Right skews are a little like this is a pretty good scenario to actually describe it. You'll see the begin is at the top and the commit is at the end for these two transactions, right? So this is just vacation time, right? And I have to have an employee working at all times, right? And so in client one, I say, I want vacation, and the app confirms that employee two will be on call. So I have coverage, right? That's great. I haven't committed this yet. But at the same time, somebody comes in and says the second employee now wants a vacation, and it sees that, hey man, employee one is actually on call. So I'm good. In both situations, it looks good. Both applications are saying this is great. Before the commit even happens, it says, great, allow somebody to take a leave. And on the other side, it allows employee two to take live. So now you don't have coverage for your help desk or whatever that is, and you have this right skews. Right skews are a little bit difficult to understand because ultimately it's dependent on the capability that you're actually trying to do within the two processes that are accessing for this database or updating this data at the same time. It's less about, it's all about timing. All of them are about timing, but it's also compiled with what you're trying to do. We see this a lot in kind of inventory. You can imagine, like, do I have enough? That sort of thing. And this is a really good situation. So again, it's kind of one of these areas where, what can go wrong will, and debugging this is, wow, what happened here? It looks like these two transactions went just fine. So when you have serializable, what's going to happen is you're just going to put a try catch block around client two. It wouldn't have committed. And by the time it went to catch it, right, like you would have tried the first one, it would not have committed. The client two would have said, hey, wait a second, I can't because this is blocked for right now. Retry it. And on the retry, it would have had the right information saying like, hey, wait a second, employee one is on vacation, so I can't approve employee two, right? And so these are the little things that can go wrong, and from an isolation point of view in a database. And quite honestly, we have implemented the top layer of this. So hackers can also exploit these issues. There's this great, if you look up this paper, acid rain concurrency related attacks on databases. There is some really crazy stuff that hackers can do to basically drain accounts based on these kind of concurrency related transactions. The paper here by Peter Ballas is pretty awesome. Peter Ballas out of Stanford. So I'm not going to get too deep into acid rain, but it's definitely something to look at in terms of, man, what can go wrong will. And hackers are looking for lots of different ways to actually do these things. So how do you solve this problem in a distributed environment? So this is the last bit, and hopefully this is valuable to you as well. Less about, it's kind of how we do it, but I'm going to talk about Raft. I'm going to talk about multi-version concurrency control and the algorithms that we use to protect ourselves here. Now, I think these algorithms, why we use them in our distributed database, are applicable in lots of ways in terms of how you're developing your own distributed systems, because distributed systems add a wholly other level of complexity here, because you have systems all over the world. And for us, it's like, how do we have one single logical database that is protected against these things? And you have, serializable isolation across every instance, every endpoint across the entire planet, and doing that in real time. It's a complicated problem to solve, and something we've been focused on really for quite some time. So it all starts with Raft, and Raft is a distributed consensus algorithm. It allows us to basically provide an atomic right? The A in acidity, right? The whole thing commits or not. And when we write to CockroachDB, we're actually writing it 3 times or 5 times or 7 or 9, some odd number, right? And when we write, basically, we're being insured because we're going to get quorum. So 2 of 3 nodes are going to actually commit a transaction. And the leader is this kind of special instance in this replica set. Like, we have a replica set of the data. We're going to write it 3 times. We aren't synchronizing data. When you start synchronizing, you get in a whole bunch of different issues around atomicity of transactions, and because the synchronization go wrong, right, between various different reasons, right? And so basically all writes are going through the Raft leader, and as long as 2 of 3 actually have committed that data, we're good, because the third one will come along, right? And so distributed consensus is actually one of these important things. It does allow us to get this kind of, a transaction commits or not, and like I said, we do that via quorum. Now, if you want more information about Raft, go check out the secretlivesofdata.com. I think this is a great visual representation of how Raft works, and much better than I can do, honestly, in a little talk here like this. Now, underneath the covers, okay, so we can make sure that things get written the right way, like it's going to happen or not. And it's going to happen in all the places I need to happen, right? Because when we write to Cockroach, we're writing it 3 times, right? And so Raft makes sure that 2 of 3 commit. And without that, I'm not gonna have a commitment, right? I'm not gonna commit that transaction. So the thing's gonna commit in whole, like the A gets actually happening, right? So these things also need to happen in order. So the serializable part of this, in terms of when things happen, so that there's no overlap in transactions, right? Like, because that's what we were talking about before. This is where we use multi-version concurrency control to actually do these sort of things. Now, this is a high-level description of how this works. If you go check out the Wikipedia article on this, I think it's pretty solid in actually explaining this, but MVCC is actually how we do this. So in any sort of transactional system, we got to think about these 3 things. Number one, there's the transaction. It's the thing we want to do. There's a timestamp for the transaction, because remember, we're going to do these things in order. We actually have to understand the timing of them. And then there is the object of our intent, which is, what do we want to update, right? So in MVCC, in a very basic flow, what we have is we have a transaction. And at time 0, we've created that transaction request, and we have the object, right? And so the first thing we do, we say, hey, let's write this thing. And what we're going to do is we're going to update, the time has gone to 1 second here. And we have 2 transaction stamps on the object that we want to write in MVCC. We have a read timestamp and a write timestamp. So at time 1, the write came in, and so we've updated the write timestamp to 1. Great. Okay, good. Step 1. Now, what happens in the background is we create a temporary object while we're actually doing these things, right? So we can maintain the original state, but we have this temporary that if something goes wrong, we just throw it away. You know what I mean? And so while we're actually updating that temporary object, what happens is when that temporary object is good, and that's going to happen at second 2, at second 3, right? We say, hey, man, this thing was good, and acknowledge back to the original transaction. Everything's good. We committed, and I updated my read timestamp to 3. So now when I have another transaction come in, I can actually evaluate the latest read time and when the latest write happened on each of those objects. So I have actually a good state at this point, right? So let's try this again, but with a conflict, because what can go wrong will, okay? So now just like we started before, at time 1, we write into the object, the initial thing. It updates its write timestamp to 1. It creates this temporary object. The temporary object is still doing what the temporary object needs to do at time 3, the upper left. At time 3, another transaction comes in. Actually, it was at time 2 on this, right? So at T2, right, the transaction stamp 2, at T2, it comes in and tries to write. Now, what it does is it looks at, the read timestamp, because I'm going to try to write this, and it says, wait a second, I don't have time, like the time in my system time right now is actually more than the valid time it is for me to read this. Because if it had actually been done, it would have been at 3, right? And it'd been like, oh, it's less than, it's fine. But right now it's in conflict. The transaction is happening before the read is there, right? And so basically we timestamped this thing, and so we have a conflict. And so for transaction 2, we need to reject that transaction. Okay, and so that's basically kind of how this works. And so long story short, it's basically ensuring that each transaction happens in order, serializable, right? And so this is what you're doing in the transactional model to make sure that these things are happening. Okay. So let me just look at this really quick. Great. Okay, good. All right. I hope that is valuable to people. MVCC is actually pretty cool. Now, code like this description of it, look, I'm the marketing guy. I can just go through and I'll describe these things. Coding this at scale across a large scale distributed system, difficult to do. Time becomes extremely important in these things. And when you think about distributed systems, here's the problem with time. Each box has a different clock. Like if I looked at the clock on this, well, Apple does a pretty good job, but is it within, is it 20 milliseconds of each other? Is it 50 milliseconds? Time becomes actually really, really important. And so when you start thinking about databases and distributed systems, the time element is actually pretty important. I know, Spanner uses, hardware atomic clocks. We actually can accomplish the same level of kind of consistency of time across various different nodes. And what we've done. We have a living without atomic clocks. We have a blog post that talks about how we do this, how we manage time in Cockroach. And so feel free to go check that out as well. So 1 second, let me just see here. Yeah, so there was a question, what happens if the clocks are not synchronized? KK, great question. You got a problem. And I think that's a key piece of distributed systems. And when you're starting to do these things, this is really one of these things that's really difficult. And I kind of just described that. And the time alignment across different pieces of the system is difficult. Like I said, Spanner's using hardware, atomic clocks. We do it in software. And as I said, there's a great blog post that talks about that if y'all want to go check that out. So how small are these time slices in real life? Well, great question, Andrew. They could be as small as 20 milliseconds, 50 milliseconds. They could be within a couple milliseconds of each other. And it really comes down to, the level of detail that you're actually implemented in the database. Now, these things are not easy, but that's the kind of time frame we're talking about. So the timestamp across different nodes needs to be the same for sure. NTP is the basic of this. So network time protocol has been around with us since like 1987. NTP is good, but also there's drift between various different sources. There's things in cloud databases like TrueTime that people use. We use NTP, and then we have kind of software that allows us to deal with this kind of logical drift between various different servers. So NTP can solve a lot of this, but it's not reliable enough. You need to actually account for some of the drift that's going to happen. So these are great questions, because time is actually a really big deal in distributed systems. When you start, it means you understand the isolation part of things, because I think the isolation part is one of those things that I'm not sure everybody kind of gives it the right cred, if you will. So, okay, so last bit, I just want to quickly go through this. I've been through this lots of times with lots of people, but like, how does this kind of work in Cockroach, right? And so Cockroach, here we have 4 nodes of Cockroach. We have a transaction on the left-hand side. We're going to insert these records into the database. I'm going to write these 3 times. So here's my transaction. That's in blue because any one of these nodes is an endpoint. Any one of them could have taken this, right? So what I'm going to do is with Raft, I'm going to go and say, hey, look, I'm going to begin this transaction. I'm going to write this record into this table. I'm not going to get into our ranges, but we basically automate all the sharding on the back end for you for this sort of thing. And what we do is in the transaction model, we basically, the Raft leader that we were talking about, they have this kind of this setting. It's like, hey, look at this transaction is pending. I'm going to set this to pending. And what I'm going to do is I'm going to take my followers. I'm going to say, hey, followers, update here. And I'm going to insert Sunny into those records. And as long as one of my followers has committed, I'm good. I've got 2 of 3. And what I have is I have kind of these temporary commits, like these temporary kind of objects that are there, basically that are the next versions of these things. So we're just basically appending a new record. And once I get the 2 that are good, and the second thing comes through, okay, my transaction is still at pending. I go to the second Raft leader. He gets an acknowledgement back. So I have 2 of 3 on the 2 writes in this transaction. I return back this acknowledgement. And the gateway now says, hey, look at this initial transaction committed. And let me make sure that all these records are now committed. So the temporary color of yellow for each of the temporary records goes in, and I've committed and I go back. Now, like I said, what can go wrong will. Lots of things can go wrong in these models. Coding these things seems pretty simple, but it's the corner cases that kill you. And that's kind of how we do it in Cockroach. Hope that's valuable to you. So somebody was asking in the chat, what were the reasons to have replication factor greater than 3? Lots of reasons, Conrad. By default in Cockroach, we replicate 3 times. So you're going to have 2 of 3 for quorum. Often people will improve or increase their replication factor to 5 or 7 or 9. And it really comes down to a question around availability. Or it comes down to, how many copies of data need to live in a particular region in terms of the latency. And so really it's a balance of resilience and latency in larger systems, Conrad, right? So like, if I want to have a replication factor of 5, but I want to tie, 3 copies of that data to, nodes in one region. So I have, very fast access to that. So I can quorum very easily, but I still have 2 copies in another region. Well, I have this higher probability of being able to survive a failure of an availability zone because they're being written in other, places, right? And so there's a lot of information in our docs about, replication factor and configuration, because geo-partitioning of data and where data lives is something that's also kind of special we do in Cockroach that that actually kind of goes to what you're asking there, Conrad. So Evgeny is asking, is Raft leader the same thing as a leaseholder in terms of CockroachDB? Yes, it is, Evgeny. It is absolutely. So that is the leaseholder. That's the Raft leader that we talk about, and it really is making sure we have these atomic commits in our transactions. Okay, let's see here. All right, so I've done that question. That is all I had, y'all. I mean, if there's any questions, I'm happy to talk through some things. I hope this is valuable to you. You can go start CockroachDB right now. You get an instance up and running. You know, we have a serverless version. Right now it's single region, so it doesn't have all these kind of bells and whistles across the whole board, but it is beta. But you get a dedicated instance, which you can go check out all these things. You actually you can run CockroachDB demo on your laptop today, and it'll simulate a 3-node or a 9-node environment. You go check that out in our docs, and you can kind of play with these things as well. So, do you have an ETA as to when we'll be able to download Apple Silicon libraries, binaries? Conrad, I'm not sure what the answer to that is. I'm not familiar with the Apple Silicon binaries, so sorry. And I work at Cockroach. I'm not at Apple. I'm loving it here. So, okay, well, that is it. I don't know if there's any other questions. It'd be great. I'm hopefully that was valuable to people. Again, thank you for taking time. I know there's a survey after this and everything, so please do, give us some feedback. But again, thank you for joining us today. I do hope this was valuable, and have a great rest of the day.